Yeah.
Okay,
Yeah,
cool.
I think it is. Okay, cool. Thanks. So, hi everyone. My name is Krewcun. I'm finishing my PhD with the Institute Pascal in Clermont-Ferrand. And so I'm going to talk to you about my PhD topic, which is the simulation of balloon expandable coronary stents. It's wait, it's in there something wrong with the slides. Okay. So as an introduction, I'm just going to give you the different parts of the full presentation. I'm going first to talk a bit about medical context to define properly the elements I'll be talking about. Then I'll dive a little bit more into the details of how did we use so far to actually perform the simulation. Then I'll talk about how we experimentally assessed our simulation, and I'll show you first results of this work. So first, with the medical context, my PhD, as Hugo said, is related to the coronary artery disease, which is a natural aging process taking place inside the arteries, and which consists in the progressive growth of a plaque inside the artery wall. In this case, we are talking about the coronary arteries, which are the arteries surrounding the heart and providing the heart muscle with blood. So the consequence of the disease is that because of the plaque growth, the blood flow towards the heart muscle is reduced, and therefore the heart muscle suffers necrosis and, in the worst case, failure, which means a heart attack. So to prevent that, a solution is to rely on endovascular intervention, which uses a catheter at the tip of which are fixed a deflated balloon and a crimped metallic device in the shape of a cylinder, which is a stent. The idea is to navigate this catheter all the way up to where the plaque is located in the coronary artery. And once it is in place, the inflation of the balloon has two effects. The first one is that the plaque is actually crushed, which allows the artery to retrieve its natural diameter. And the second is that at the same time the stent is expanded and put in contact with the artery wall. One specificity of stents which are deployed this way is that they remain in a deformed shape even when the balloon is deflated, which means that there are devices that patients keep for the rest of their life. The interest we have of simulating this type of intervention is to provide the physicians with a prediction tool which would be useful in particularly complex scenarios. For instance, if the stent has to be opposed at the bifurcation of two vessels, or if the plaque is overcalcified, and therefore will resist the stent expansion. The fact that we want the simulation to be integrated into a clinical routine imposes that it has to be fast. Here we are not necessarily talking about real time, but definitely we have to be under a few minutes as for the computational time. And of course, it has to be reliable because we want to influence medical decision. So now I'm not going to give much detail about our methodology, but I'm rather going to focus on the way we use so far in the implementation of this simulation. So first, very briefly, we use a lot of SOFA components without any modification. So this includes solvers, the use of constraints of the collision pipeline, of markings, of the flexible plugin for the behavior of the artery. So this is really interesting because we could use them very easily and it saved us a tremendous amount of time. I'm talking of the last one, which maybe some of you know already, which is the component in which I implemented finite beam elements, which are elements, one-dimensional elements used to represent sender structures. The reason I'm stopping on this is that a specificity of our method is that we used connected beam elements to actually mesh the global structure of the stent. This allowed us to compare to three-dimensional elements to greatly reduce the dimension of the problem. Now, the thing with the beam FEM force field component is that it's limited to elastic deformation, meaning that these elements, when subjected to deformation, tend to go back to their rest shape. And if you remember earlier, I said that with this type of stents, the deformation is permanent. So this corresponds to a different mechanic phenomenon, which is plasticity. And therefore, we had to add an additional plastic behavior to the beam elements. So I won't go into really the detail of plasticity theory because there is a lot to say about this. But just to give you an insight of what we did, the idea of plastic behavior is that if you only consider an elastic deformation, it is, well, a linear elastic deformation. It is characterized by a linear relation between stress and strain in your material. And what happens with plasticity is that at some point during the deformation, part of the deformation becomes permanent, and at the same time, the relation between stress and strain becomes nonlinear. So we had to add a few elements to model this properly. The first one is a yield criterion. This is simply a function which tells us when does the material switches from an elastic range to a plastic range. In our case, we use the von Mises yield function for that. The second one is how we can keep track of the plastic history, because as the deformation is permanent and the relation becomes nonlinear, we have to keep a track of the history of deformation. The idea for that is simply to divide the strain in two different parts, a plastic permanent part and an elastic part. The second element we use, the flow rule, is simply what describes the evolution of the plastic permanent part of the strain. In our case, we use an associative flow rule, which means that it's related to the yield criterion. And these elements, we use them in an algorithm which is famous in literature for modeling plastic behaviors, which is the radial-return algorithm, and which, unfortunately, I won't be able to develop more, but if you have any question afterwards regarding this, we can, of course, talk about this. I'm just saying a few words about Python scripting, because we use a lot of Python when doing the simulation. So through using the SOFA Python plugin. First, we use this for the scene initialization to use scene files described in Python, but mostly to parse the stent topology from a mesh file. And the procedure description of things we could do with Python was very useful in this matter. And then we also use a lot of Python to dynamically control the simulation, mainly the way we model the expansion forces, which are in reality created by the balloon, and also to access the mechanical objects in the simulation. Regarding this, I'd just like to say that I'm very interested by the modification we talked about this morning regarding SOFA Python 3. So another important part of our methodology is that we wanted to assess experimentally our simulation to check its precision. So the idea for that was to use microcomputed tomography acquisitions of stent deployments. So we deployed stents inside of a micro CT scanner, and we performed acquisition at different steps during the deployment of the stent. For instance, when the inflation pressure was of 2 atmospheres, 4 atmospheres, etc., until the nominal pressure. This allows us to retrieve three-dimensional geometries of the stent at different steps during its deployment. And by registration, we can compare this configuration with the corresponding configuration we extracted from the simulation outputs. Now I'm going to briefly show you a few results. So first, I'll show you a brief insight of what the simulation looked like. So this is a very simple example with a straight cylindrical artery. And you can see that the stent inside is expanding. The balloon is not modeled directly here. We use very stiff springs to actually mimic the action of the balloon. And we can see that under the action of the springs, the stent is progressively expanded with a change of color, which corresponds to the switch from an elastic deformation to a plastic deformation. So at some point, the stent is put in contact with the artery wall, which is also model, which is elastic in this case. And when this happens, contacts are detected and resolved thanks to the classic collision pipeline of SOFA. So yeah, here directions of corresponding to these constraints, and I stopped displaying them because, of course, all the nodes of the stents are eventually put in contact with the artery wall. So from this simulation, we can extract, as I said earlier, geometries, which we can registrate with the micro-OCT outputs we had experimentally. So this is directly the example I took from the video you saw earlier and the corresponding experimentation. And the metrics we measured on these outputs were both the radial distance, the mean radial distance over all the nodes, simulated nodes, and the Euclidean distance. And we can see that in both cases, we are under 100 micrometer, which is actually the thickness of the stent wires. So regarding the application we are aiming at, this precision would be sufficient for our applications. So to conclude, what we did was to model the stent expansion using serially linked beam elements and adding to them a plastic behavior to model the permanent deformation. Another important point, as I said, was the assessment of this simulation with ground truth experiments. If you're interested, this led to 2 conference publications this year, so which contain much more detail than what I said here. And don't hesitate to ask them if you'd like. To finish, currently we are working on 2 main things. What we are doing really at the moment is the generalization of the experiments to more realistic curved artery geometries. And the very long-term goal of what we are doing would be to use endovascular OCT images to retrieve personalized artery geometries and use them directly in the simulation to actually perform patient-specific simulation. So that's it for me. Thanks for listening, and if you have any question, here to answer them. Thank
you. Is there any question? So yeah, in the video again, I think you mentioned that, again the blood vessel that you could see surrounding the stent is actually deformable. Just here, the deformation is very small in that case. The stent comes in collision and put the pressure on the blood vessel, which is actually moving, I think, a bit less than a millimeter. Or
yeah, because what happened here is in the experiment we expanded a stent which nominal diameter was 3 millimeters in a 3 millimeter diameter artery. So
with a bit of fat maybe on it, or not yet?
Not yet, no. But so there is a slight contact, but afterwards the deformation of the artery remains very minimal.
Is there any, yeah?
So why OCT imaging for the validation instead of X-ray based?
Actually, OCT images here is specific to cardiology. There are technologies which allows cardiologists to retrieve 2-dimensional images of the inside of the artery using OCT probes. And the corresponding images are of a very high resolution, meaning that they are comparable to histologic images of sections of the artery. What happens is that in Clermont-Ferrand, the physicians have an important base of these images of coronary arteries of real patients. And what we'd like to do is to exploit the high resolution of these images to get the artery geometries. And yeah.
Any other question? No?